All right. So Elasticsearch, they had a redesign recently, and the homepage is really pretty. So I'm just gonna showcase that. Oh, that didn't look so good. Where's the other one?
You clicked at the
Products.
advertisement.
There. Yeah, here, look at this. It's all like animated and super pretty, and videos and rockets and dogs. Um,
And
yeah.
Antonia goes all fangirly again.
Psst, we're recording. Yeah, no, so Elasticsearch. Elasticsearch is based on Lucene. And do you know Lucene, Waldo?
Nope.
All right. So Lucene is kind of old, and it's a search engine. I think even Google uses it, used it. I think they wrote their own now. But Lucene is an old search engine. Shit, now Flo's going to say lots of stuff. That is basically working around creating indexes for the things you want to search for often, and thus making everything really, really quick. I don't know if you know this, but in MySQL, by default, there are hardly any indexes, meaning the data is just stored in its tables and its columns and everything. And if you want to search for something, it has to actually look through each row of the table that you're looking into to match whatever you're looking for in your query against each record, right? And that, you can imagine, can become really, really slow, especially if you have a lot of data. In the beginning, you don't really notice it. MySQL seems really, really fast in the beginning. But the more data you have and the more it has to go through and traverse, to check against your query, coupled with the more complex your query is, that can create really, really slow queries. So they've created something where, by default already, the primary key always has an index. What index really means, it's something you can't really see, you can't really get into it really. Maybe, binary stuff, maybe you can actually check it out in some way, but the index is it's almost like a key value store somewhere else, where a specific property, like the ID, is all of the IDs are stored somewhere else, so that and okay, wait a second, and the record of the original table, I think the index of that record or something, so that very, very quickly you can, from looking through the index of the property ID, find the records really, really quickly without actually having to compare each row. Something like that, isn't it? Or is it even, maybe it's even one better, that you can actually look, if you say you have 3 records with an integer value of 5, and then the rest has some other integer value. And then the index of that specific property would look something like 5 is in row 1, 2, and 3. Or, something like that. And then immediately you can fetch those records. Something like that. I actually don't know how the internals look like, and I'm kind of looking to Flo to explain a little bit more in detail, but the indexes work something along those lines in order to facilitate and make it much, much quicker to find records based on specific properties.
I'm not completely sure, but I learned about this in the university, and there they explained that indices are just basically another table that's just ordered in a very, very, very good way for searching for this certain column, kind of, or
Yeah, in MySQL, it's like, it's a sort on the column.
Okay. Well, I guess it
But I
depends
don't.
on the technology, right? And MySQL is probably different than, I don't know, even if MongoDB has indexes, but if they have, they probably do it differently, and then Lucene does it again differently.
Yeah.
So
So
the basic
indexes aren't the
premises,
same.
yeah, indexes aren't the same, but the basic premise is there's a way to point from specific properties and their values to the actual data without having to actually look and root through that data. And that's the benefit. However, they do it technically in the end. And so MySQL doesn't only add indexes for the primary key and that's it, but also you can add deep, custom indexes on other properties, obviously. But you can also, and that's where it really becomes interesting, you can add indexes for combined properties. So you can say, I always query, like, for instance, an entity class and an entity ID together against a specific table with their rows. And if that gets slow. But if you index those together, then if you were ever to look for instance, I want to find, what's the SCORMED equivalent? I want to find products from the product table. I want to find those that are both from a specific product type at the same time as that they have category med, for instance. And if you want to look at those two properties together, the product type PVS together with the category med, and you would index those together, then it would, in, I don't know, really, really fast, find those records. So again, MySQL doesn't really have a drawback here. Again, MySQL is fast if you create indexes for it and if you let it do that. Even there's an interesting anecdote here, is if you were to create an index after the fact, it works, right? You can have tons of data, thousands of records, millions of records, and then add an index afterward. But then it becomes, like the CPU of the machine goes way up in the moment that it has to create those indexes, because in that moment, you can imagine it has to traverse through all documents, right? So it's like a really heavy load query in that moment, creating those indexes, but then afterwards, searching becomes really fast again. So we've once almost shut down a production system because I was just going to create an index, for a table that we often query. And, the hoster called and was like, what are you doing to the server right now? Like the MySQL process is using way too much CPU. And I was like, sorry, creating an index, wanted to make things fast. So that's something to consider. But really, MySQL doesn't yet have a drawback. But then there is the drawback, unfortunately, that MySQL is pretty slow still for full text search. So basically a like query. If you search anything with a wildcard or any sort of, not regex really, but yeah, wildcard in a like query, it has a really, really hard time because you can't really index that. In order to index that, you would have to index the part that you assume is going to be searched for. Like, let's look, for example, at a string like my home is yellow. All right. And you would create a like query that looks something like this. Yeah. Then the index of that string could be that you say, I want to index the entire string. So let's call it index 1 is the entire string. Index 2 is each single word separated by the space. Could be a reasonable indexing of this string. And of course, you can imagine that this can get really large. The index for this string property, let's say this is the title property, yeah? And then it's the title index. So title index 1 could look like this, or we would call this index maybe raw to speak a little bit Elasticsearch. And then this would be the title index for words or something. And then would be, I don't know exactly how they look like. We can look at it as though it were an array if you want. So we would have each word as its own index. So if you had a second record that also has a title, misspelled now. If you had a second record that also has a title, and that title was the yellow dog, then all of a sudden you would have two occurrences of yellow, right? So the index for yellow would hit 2 rows instead of 1. So this would be document 1, and this is document 2. And then the index for the title index word for yellow would then point to 2 documents, this one and this one. And then if you would make a like query on the yellow, it would actually, hopefully, quickly find both of those words. So that way we could fix it for this use case. But what if you want to have this kind of use case? Like a sort of an almost autocomplete sort of use case. How would we have to index this now? We would have to index it, what? Like part words? Like every 5-letter words? Or, it becomes really, really strange, and you would have to sort of start these crazy indexes that, in the end, do slow MySQL down. They require a lot of space on the hard drive, as you can imagine. If you have a lot of records, a lot of titles, so it's a lot of hard drive capacity used for this. And also, I'm personally not aware if this is performant or not, but it's at least not what MySQL is designed for, or if it even can do this kind of thing. Word-based indexing or trigram-based indexing, or just like certain letter combinations or whatever. I'm not even sure if it can do that. So where I'm standing, like queries should be avoided. And if they should be avoided, then that means we can't really solve some problems that some clients may have. Oh, I think I might have been lagging out there. Have you?
No, you were good.
Yeah, okay. So there might be some problems that we can't solve with MySQL, such as autocomplete search or like on-the-fly search or something. Let me give you a quick example of a project that we've created where we use a lot of these like inline queries. And so here's oh god, these are all bullshit names. Let me take something that looks a bit better. Okay, so here we have something called Metallfacharbeiter. So let's say I want to look for the word Fach now. And what I want is I want to find those where the word is included somewhere. Yeah, and see, here it is actually a full entire word inside of these braces. Here it's also a full word. Here it's part word of this long one. Here it's also a part word, yeah. Here somehow the coloring didn't work. The highlighting didn't work. I don't know why. But you see the thing that's going on here. It finds it kind of wherever. And it would even go so far as to look inside of, like, for instance, München, like the street. It depends, or the city, I mean. It depends on, of course, what we've selected. This is all Elasticsearch. But the idea is that we have possibilities and we can solve problems that our applications need to fulfill or need to solve. And like queries in MySQL just don't do this. So that's a quick introduction as to why we even want Elasticsearch in the first place. And then we found another thing with Elasticsearch that's kind of nice. Since Elasticsearch is an object-based storage, looking a lot like JSON, or it is JSON really, not the storage itself, but the way we communicate with it, we can actually deep nest properties, which is also something we can't do in Elasticsearch, in MySQL, I mean. So for instance, say we have an application configuration or whatever. In MySQL, we could only add strings or integers or dates, and that's pretty much it. But in Elasticsearch, in Elasticsearch, we can put in an object here or an array, or we could do anything. And then this object could in turn include some ID, or it could be as deep nested as you want. Pretty much just a regular JavaScript object. And that's another advantage of Elasticsearch, because sometimes the data gets so complex that it's nice to organize it a little bit. And putting things into objects or putting things into arrays is just a way to organize it. You could also write down like application underscore ID and then make it a literal value. But it's just a little bit more organized this way with objects. So that's a nice that's another nice advantage. So anyway, let's look at some specifics of Elasticsearch. Elasticsearch runs in the background as a service. It's a little bit like MySQL. You can either have it running really as a true service when you boot up your computer, or you can have it running like I do, command line, just starting it up, and then it's running in the terminal constantly.
And you can also include the Elasticsearch in a Java application. You can include it as a jar, and so you don't have to start it separately if you
That's
want
also
to
cool.
use it. But for the hosting, it's better to run it as a service.
Yep. And okay, so what we can see here, we see the initial output, and we see that it's starting something up, and we see here there are several ports going on. There's 9,300, and then there's the 9,200. So there are 2 ports, and then there's some other stuff with what it's binding to, right? It's binding to my IPv6 and my regular IP, IPv4. That's probably what this means, and then my local host and all that stuff. So it's binding to a bunch of things, but really it's doing these 2 port things. So only one of them is the HTTP version. You can actually access Elasticsearch entirely through HTTP, but only one of them is the HTTP port. The other one is the internal port. And Elasticsearch is based on Java. So the one is like a Java transport port. transport port. And the other is the HTTP port. And it's the 9200, that's HTTP. So actually, by just navigating in your browser to localhost 9200, you access now your Elasticsearch index or your cluster. It's giving us a name. This is randomized on startup. It's called KISS this time. If I restart it again, it's giving us a different name. And the point of that is to, if you have multiple instances running, they can run in parallel and they can sync with each other. I think it works something like this. I'm not sure. I'm going to try something. If I run this again now, it's going to I think it's going to look for different ports and it's going to have both of them running. Is that what it's going to be doing? No, it's not. But I think I can set that somewhere, which port it should be running on or something. And then it synchronizes each other and then they work together. So now the name should be different. Yeah, Kendra. And yeah, my guests are here. So I'll just make a quick interruption, 20 minutes, and I'll be right back, okay? Okay. Yes, so this instance now is called Kendra, and the cluster name is Elasticsearch, and I think there's also a naming conflict with the cluster name. I think, no, the cluster should be entirely everything. I'm not exactly sure. Anyway, you can run multiple instances, and then they run on different ports. Okay. We see something else. We see that the version number of this Elasticsearch that I'm running is 2.3.3. A quick info about that is that currently Elasticsearch is on version 5. However, the 2.3 is actually the previous stable. So we're running on the stable version previous to 5. 5 is pretty great though, and it's really great, and we want to switch to that. And I think in Basics Dialog, we are using 5 also. But in K-Center and other projects, we're still using 2.3. And then internally, it uses Lucene version 5.5.0, which I don't know nothing about. I have no idea if there's a newer version or what that is. I just assume that Elasticsearch makes good choices about that. Lucene, which Elasticsearch is built on top of, is the actual index store. Okay, so that takes care of things like indexing my and home and is and yellow and matching that to documents. Elasticsearch is the layer on top of that because Lucene is actually quite hard to use. Lucene is not very, it's not very straightforward to work with Lucene. And people have sort of shied away from that. Elasticsearch makes it really easy to work with Lucene, use Lucene and its strong engine, and still have very quick to learn and easy to manage HTTP requests that, that just feel part of the work process, just like you would make an HTTP request to your server or somewhere else. So you don't have to learn anything new. It's just HTTP. All you have to learn is a little bit about how you query things in Elasticsearch. But okay, so let's go from this and let's think about that. We currently, let's imagine we don't have any data in it yet. And if we don't have any data, how would we create? How would we mimic this? We want to organize our data, right? So we would want to mimic this table database structure that MySQL has. Unfortunately, there is a bit of limitation when it comes to that. So what MySQL does, it has a database, and inside of that database, it has tables, and inside of those tables, it has columns and rows. But Elasticsearch has only the cluster, and in that cluster, it has what is called an index. And an index is a named grouping. It groups together documents. That is true. It groups together documents under one sort of namespace. But there are still things that are shared across those. So you can, for instance, you can, for instance, search across multiple indexes at the same time. You could create a search that fetches all records based on a certain query across multiple indexes, something that you can't really do in MySQL. So it's kind of still acts like one large thing. And it sort of goes along with the idea that when you're hosting a serious application, the instance of Elasticsearch that's running on that same server is actually it's responsible for only that single application, right? So you would have one Elasticsearch running for that entire application, and would be even possible to cluster it across multiple servers just to have, I don't know, petabytes of data across multiple servers and have one single application using all of that data. So, the MySQL feels a little bit like localhost wise, it's nice to have multiple databases, but once you're in production, you kind of also only have one database in your entire MySQL and maybe one for PHPMyAdmin or something to host a serious application. So it's kind of, I guess, those same lines of thought. But just so you know, there's kind of no database structure really. You dive right into tables, and those are the indexes. So let's look at an example of that. I happen to have some data. So let's look at an index called contacts. The mappings that I'm calling here, the underscore mappings, is not actually like a property or something that I've created. It's something that's always there. And if you on an index call underscore mappings, it's like you want to look at its mapping. And a mapping means you look at how each property is stored inside of the contacts. So for instance, we have a property called city, and that's of type string. There's some other complicated stuff behind it, but really it just says, I am aware that in my contacts index, there are documents that contain a property called city that is of type string. And it also contains a property called client, which has sub-properties, ID, imported ID, and name. So this syntax basically means I think this either means it's an array or an object, but I think it means it's an object, what this mapping means. It's kind of confusing because the outcome is an array, but I think this is a typical object mapping. Here's another one, country is string, so those are easy again. And here's an object, yeah, so see it's the same structure. So here's clients and properties, and here's created by properties. So created by is the representation of a user, not the entire user, but a lot of that user. Think about it a little bit as the way you output JSON stuff in a marshaller. You also sometimes want to put extra data inside of data. Like for instance, you want to the creator I guess the creator of a product. You might want to, or the blog. Yeah, let's think about like blog entries, for instance. That makes sense. So the creator of a blog, you might want to give just basic data about him. Maybe like a picture source, so you can you can make the picture visible in the browser. A name maybe. And then maybe a link to his profile. So you need the ID to be able to link to his profile, something like that. So you would want like a small compact object inside of the actual blog object. And that's kind of what's happening here. So we have a created by where we include a color to make a little name tag colorized, and then a display name, an ID, a name first, and name short. But this isn't actually the data inside of any of the contexts. This is just the mapping that's showing us what the data is supposed to be like. It's sort of restricting us to put in the country anything but a string. We cannot put anything but a string into the country field now, because it's kind of restricting it that way. So in a way, it's a little bit like the table structure in MySQL, what we're looking at right here, this mapping. If we look at the search instead, that's the endpoint to actually fetch the documents out of an index. So now we're looking at the index contacts, and we're looking at all the records inside of search, but not really. We're actually looking at a total of I'm not actually sure how many we've fetched. I think it's default 20 or so, or 10. Let's see. It looks like 10. So it's giving us default 10 records if we don't specify otherwise in the search, but it has a total of 30,000, as you can see. So I have 30,000 records in this contacts index, but it's only giving me 10. If I would increase the size, like let's say like size equals 500, then it takes a little bit of time. The data's not loaded. Now it's processing it with this plugin that I'm using to make the JSON nice, but it went kind of quickly, even though it's 500. And I could, up that to 5,000, and it would still be relatively quickly. It's not, what's taking most time is actually, getting all that data into the browser. Like basically downloading the data. But Elasticsearch is quite quick to respond with the data. And now what you can see is that it's like processing it in the plugin to make it just pretty. But the data's already there. Okay. And what we should be seeing now, I should actually remove this just to make it a bit more snappy. What we can see in a moment, is that we have those properties that I was talking about. So we have, for instance, in a client, which is an array, which wasn't clear in the mapping. And I'm going to tell you about that in a second, why that is. But here, the client is an array, and there should be like a created by, which is a user. Created by? Come on now. Okay, how about we create our first query to find all records that have a created by in it. So we can actually show that. The way you create a query is you actually add a query object to this search request. So the search request is just the default, and what I just now did, I did like a little inline query with the size. That's like basically a query parameter, but right in the URL, and you can do that. That's no problem. I think this is called, oh, Jesus Christ, what is this called? It's called quick something. Quick search? Quick query? I'm not exactly sure. Let's see. Elasticsearch quick query. Query sting query DSL. No, this is already the entire object structure. Anyway, there's this shorthand where you can put it right in the URL, but it's not like you really use that ever. I just wanted to make it so that we can quickly look into data. So let's go into the complex way of doing it, and we could do it with a curl. I don't know if you know curl. It's basically like you do an HTTP request over your console, but we can also use something like this DHC, which you guys have probably been using a little bit now with the other REST with the basics dialog. So we can just dive into that. I think that's going to be nice. So what you want to do is you want to post some data to the search request. Seems weird because you're getting data, but that's what you want to do. You want to post some data because you want to have a body to post data in. And we're going to remove this authorization. And here is where we build our query. Okay. So if I just give in an empty object and do this post request, I'm still getting the entire data. I'm getting all hits and all data just like before, the 10 documents. But I can now do some querying. And there's a very specific syntax to Elasticsearch, and if I don't know it by heart at all. And there's a tool. I mean, I could use DHC, and I could actually, you know what, we'll do that for now. I'm just gonna build this. I'm just gonna build queries based on the documentation. I think that's gonna be nice. So let's use a let's use an exists query, not full text. Match all. Term level query, term exists query. So we want to find all record where a certain property exists, okay? So we're going to build this query exactly like it is here. We're building an object. They're actually using a get here. I heard that it's not supposed to be a get. But it does make sense, because you're getting data. It is conform with when you get data, you're supposed to do a get request. If you update data, if the server is supposed to update data, then you do a post request. So it kind of works, but it's sort of an in-between, right? Because you want to post data, and I think if I actually switch this to a get, I can't even put any data. XHR doesn't allow payloads for get requests. Well, see, it's also so it's against conformity a little bit to use get as well. It's kind of a difficult situation. I'm using post. It makes most sense, I think. So we want to build a query that checks if a certain property exists or if a certain field exists, as I call them. I call them fields. And we want to check on the created by. Is it with underscore? We'll see. We'll find out. So it found no record, so it's probably not created by with underscore. Let's try this. And it found one record. Oy. Okay, let's look at this. Okay, and we can see here an object that has these, just very similar to the mapping that we just now saw. So we have an object that contains name last, ID, color, just like we saw earlier. And so this is an exists query on a field, and we can combine that with other queries, and we can create like and or combinations and stuff. And in order to build those, I personally prefer a tool called Kibana. And also to inspect which tables or which indexes I actually have, I use another plugin called Kopf. So there are two plugins that I use very often together with Elasticsearch, and they don't come pre-shipped with Elasticsearch 2.3. They come, however, not Kopf maybe, but Kibana comes pre-shipped with Elasticsearch 5. So that's nice.
Hi.
Or?
Kibana is a separate
Oh, it's
thing
separate?
you need to run.
Okay.
Yeah, it's in the Elasticsearch 5 stack, but it's a separate
You still need to install it.
project. Yeah,
Okay.
and you need to run it in parallel.
Okay, just
And
like I have to do
yeah,
now, so that's nice.
Elasticsearch 5 don't support plugins like Kopf.
Maybe they have another way. Maybe Kibana works also. Because Kibana, it shows also these your indexes and stuff. So that's also nice. I mean, what are we using really Kopf for? I can show in a second, but it's really a little bit like just maintaining your indexes, just that, creating aliases and stuff.
Yeah, the Kopf plugin is also available now as a separate project. It's a fork. Then you can run it. It's a little Node server or a Java server, I think, and I will link it to you or in some channel.
Okay, cool. So what I have somewhere, let's see, tools. Yeah, tools Kibana. Here I have Kibana. And I had it's kind of weird that it's split, but here I have Elasticsearch. Oh no, probably this is, well, see, it's not split then. I just had a copy of it here. So I am having Elasticsearch here and I have Kibana here, and both are executable. Just like I've executed Elasticsearch, I can also execute Kibana, and I'll do that real quick. I have it preset in my bash. And now it should be running. And it's also available through its own port, which is the 5601 port. And in there, I can then build queries, and it also stores your queries. It's a little bit like when you use MySQL queries and you build them in IntelliJ, where it stores your queries over time, etc. It's kind of like that. So I have all these queries from, I don't know, super long ago, still in here, which is kind of nice. And in here, it also supports get with a payload. So it supports it like it is in the documentation, maybe not, not REST conform or XHR conform, but in the end, as long as we get the result, that's all that matters. So let's do a post request to contacts search and give it the same object that we now created in DHC with a query and the exists, and it should give us just the same. And oh, sorry, wrong port up here. And again, all right. So up here, you can switch out the server. Sometimes I'm connecting against production servers immediately, so that's why there was a different port here. But usually, you'd always have the HTTP default port 9200. And in here, we can see I had the one record found again, just like in DHT just now. But the magic of this is, if I start up clean again, I have autocompletion of these queries. So if I would start up writing just query, you can see I now it auto-completed for me, and now if I say exists or exists, oh no, it doesn't do exists, so that sucks. Term though, like I could make a term query, and then it would build up this query for me, showing me with these uppercase letters which values I still have to put in. I have to put in the field, and I have to put the actual value, and this is plumbing. This has to be here, right? And it shows me with these all uppercase letters. And that's kind of neat. So that's why I kind of like Kibana, because then you don't have to always consult the docs for every little question that you might have. So before we talk about the different types of queries that we can write, exist and term and combining and Boolean queries and all that stuff, I think it makes sense to look quickly into why the updated by looked exactly like the clients in the mapping, even though they are different. The updated by is an object, the clients is an array. The reason why they look the same is because Lucene can't do objects, and Lucene can also not do arrays. Lucene is a little bit in that way like primitive, a little bit like MySQL. And the way that so Elasticsearch comes between your data structure, telling you kind of it's allowed to have arrays and it's allowed to have objects, and we handle it for you, yeah. And it comes there in between, and it translates this into something that Lucene can actually use for indexing. And then once Lucene finds the results and finds the documents, then those documents are then responded again in the way that you index them, in the way that Elasticsearch provides for you. So Elasticsearch is like an in-between layer, like a middleware between Lucene and your actual data that you want to index. And it makes it possible that it looks like this is an array, but in reality, what it looks like in the index is something like this. So this is not the indexed data itself, but just the data represented in Lucene. And the data represented in Lucene is actually something like this. It's updated by dot name last, so it makes like a sort of a fake object structure, but since it doesn't know about objects, it's all good. Where it would say null, I guess, in this case. And then it would have, it's fine. And then it would have the display name short, and that would be ADM, and so on and so forth. Yeah, so this is the object structure for updated by. And the structure for clients looks very, very similar. And that's why the mapping was the same. The structure for clients looks like this. Clients.id equals an array of IDs. In the case of this, it would only be the single ID, but it could potentially, since it's an array, it could potentially have multiple clients in it. So then it could have multiple IDs indexed here. So that's how that looks like. And then the name would also be an array. Or not an array, I think maybe it's comma separator, right? Exactly. Maybe it does support flat arrays. I'm not exactly sure. But anyway, this is how it's represented. And something like this. And then so on and so forth, yeah? With multiple data being put into these arrays. So that's why the mapping looked so similar, because the client is treated as an object, just like the updated by is treated as an object with subproperties. Even though then these subproperties are arrays. And here you can already gauge the first problem with indexing arrays as these objects or these collections, yeah, arrays full of maps, because if each property is indexed this way and you have multiple of them inside of it, and one would have a missing property, like say the name would be missing in that one, then and you have a third one that then has a name again, it becomes sort of difficult to match this one to this one to which one? Nothing. I guess it could have made the choice, they could have made the choice to put a null or something there, but it's not clear whether the property is null or doesn't exist, and that's a difference. Is the property there but just null? Or isn't the property at all supposed to be in that piece of data, right? So if you actually don't put it in, then there would be a mismatch of the amounts of IDs and names. So that's sort of a drawback from indexing arrays as these object structures. But I digress. That's at least the reason why the mapping looked exactly the same for updated by and clients, even though the one was an object, the other was an array. Okay. Any questions so far? You want to take a break? Do you want to, I don't know, ask some questions before we dive into the different query types?
No questions. I'm fine to go on.
All right. Okay, we've already touched on exists query, which checks if a property exists or is null. So that's treated the same. If I were to look for instance, country, then I would not get any null values either. But empty string apparently, as you can see. Empty string is apparently treated differently from null and non-existing, but the exists query does take null into consideration at the very least. That's the one. It's pretty simple. Term query is also quite simple. It checks for an exact match of or that's at least how it was. Let's think about this. Okay, a term query. Let's go for this one, a type. And I want to look that the type is contact, okay? So I'm checking the exact string now against itself or against a person, specific value, contact. And now it found certain matches, I don't know, 30,000. And I'm going to do a test, I'm not sure. Let's take some letters away. Okay. All good. Yeah, okay. The type query, but isn't the type query though a little bit aware of full text stuff? Let's look for a string that has multiple words in it, like the client name. Okay, let's do a type query against the property clients dot name. Yeah, this is the syntax, like we know, like we've just learned, and we also get auto completion, by the way. And here are these other things we haven't looked into yet. I want to talk about that in a second. But I want to find all of those that contain the word AG, and that should now have some matches. No, okay. So then we can conclude a term query is an exact match query, which is good. It's supposed to be. But in order to do full text search, you use a different kind of query, which is, I don't know actually what it's called. Let's look it up. We do not want a prefix query, not a wildcard query. We want to have a full text query. And that's the match query. Yeah, right, match. Okay, good. So we want to say, let's actually have us autocomplete this, okay? Let's type match. Exactly. And we here get also autocompletion. What was it? Client dot name. And we want that to be AG. Then we hit it off. And then all right, we find 2,300 records. And here we have TUI AG, and then the next record would be Transpac AG, and so on and so forth. The default string mapping, at least in Elasticsearch 2.3, yeah, and I think also 5, the default string mapping or indexing works already by splitting the words. So the very simplest indexing example that I gave you earlier, where it splits the words up of the "my home is yellow" sentence and indexes each one, that's already default in Elasticsearch. So I can just look for one word of a string value, and it already finds it, super speed. What it cannot yet do, and this is what we're going to look into now, it probably won't find this now. It found them, but maybe they're actually called something trans. Okay, so this is full word trans now. Let's do something a little bit more. GMB is probably not gonna just be a single word. Still 4. Okay, but 4 matches, that's not very many. It's a lot of, we have a lot of contexts. So, oh Jesus Christ, there's actually stuff with GMB. So, but what we can find is it actually looks for the entire word. It has to have the entire word in its index. But we can improve on that. And we've improved on that by saying when documents are indexed into Elasticsearch, we don't only want to index them in this default way. Because this default way also kind of sucks. Because if I would run a match query, or a term query should be different. But okay, if I run a match query, no. I'm wondering why sometimes in the code we have term queries that don't give us matches unless we use the raw field. It doesn't matter. I'll look into it later. Okay. The match query gives us the ability to look for parts of a word if they are indexed that way. And we can adjust how we index data. And we did that on index time. So we told all string properties, Flo created a template that said anytime Elasticsearch finds a document that has a string property that is new to it, that didn't have this string property before, it should index this not as a string, but as 4 sub-properties. And I'm going to show you how that looks like. So the localhost 9200 contacts mapping, it's the stuff I folded in earlier. If we look at the city, for instance, the city main property, yes, it's a string. So if we actually do a match query against contacts.city, we get all the default behavior of Elasticsearch. But if we want extra functionality, we can use subfields inside of city. So they are actually nested underneath city, and they are indexed differently. We've created I think these are called analyzers. So we've created a couple of analyzers. One is the auto analyzer that that indexes words to be autocomplete searchable. What we mean by that is, let's say you have a long word, like car manufacturer. It wouldn't be in English, but in German we have that very often, that we have these mega long words. So in order to look for car and find this record, there are different strategies in order how to index this. And this was a lot of trial and error in the beginning, how to index these properly, to find, what people might be looking for. One is the trigram approach. So before we go into the auto, the trigram is an interesting one. The trigram always indexes things in triplets. So car is indexed, and arm is indexed, and Rama is indexed, and what's the next one? Man is indexed, and so on and so forth. Yeah. So these are trigrams. Always in little triplets are they indexed into the index, and then every record, every document that has in its, what are we talking about? City. Okay. Car manufacturer doesn't make any sense in the city, but okay. Any city that has any indexing of car in it, or arm or Rama, will then be a hit if I look for exactly this string. But it has to be exactly this string. The moment I look for armor, it's a little bit difficult because it depends on if I want to have exactly that hit. If I want to have exactly that hit as an index, found in the index, then I won't have any hits now if I only index it this way. There's a trick to it though. And the trick is that even my inputs that I search for are run through an analyzer. So what can happen is that even my string is converted into trigrams, of which arm is one, and the other trigram is rumor, whatever. And those two would then be searched for. So instead of actually searching for the exact string I put in, this is something that you can configure. But it's default that the property you look against, the same analyzer is used for the data you put into it. So your input data, your search query, is actually analyzed and split up into the same pieces and the same sort of formatting and indexing that the actual property is indexed into. And that way you do have a match now, right? If you run it through the same processor. But if you don't, if you say I want to have my query term be raw and be run against the index, then in this case now with the trigrams, you wouldn't actually have a hit. So trigrams is one way to index your properties. Another one is I'm actually not sure what the sort one is, but the raw is hopefully clear. Raw is just the actual entire word raw, as is. That's where my confusion came earlier. Why we would need a raw property at all if the term query does exactly what a raw property, like, looks for the raw property as an exact match. If the term query already does this, we don't even need the raw property. So I'm confused because sometimes we've had issues with this, where the term query also treated it like a match query. So this, I don't know, it's just a little confusing. I'm not exactly sure, but let's assume that there are some issues where you, at one point or another, want the entire string raw as is to match it one-to-one completely. And if that's the case, we have created a field, also an indexing type raw, to each string. The next one is German. And German is kind of weird. German, actually, it has a dictionary in the background that knows typical German words and uses the German stemmer to, first of all, split up words in a smart way, because we have these weird long words in German, like Adler, Kopf, all right? That's the head of an eagle. it would know that Adler is a word, and it would know that Kopf is a word. So without brute forcing any trigrams or anything, it would actually just split it in a German smart way by their German base words, Adler and Kopf, without any mathematical, how many characters, etc., etc. And that's what that is for. And also, it's for something else, which I just mentioned earlier. It's for the stemming. Say you have, for instance, I'm not sure if it's that smart, okay? But say you index the word Bäume. So the title of something is called Drei Bäume or whatever, yeah? Which is 3 trees. But Bäume is spelled entirely different than the singular, which is Baum, which has, it's one letter less, and it's actually an entirely different letter here in the middle. They're in really these two letters, they're not, related to one another. Not if you look, at what they're consistent of in the base. So, in order to have those two things connected, there needs to be a sort of a matching library. And this German analyzer that we've installed, it had to be installed and everything. In its dictionary, it also had that Baum is the root version of Bäume. So whenever there's an index of Bäume, it'll actually also index it as Baum. And then if you look for Baum, it'll find it. It'll have a hit. So don't think about this as a search time thing. It's not when in the moment you search for Baum, it also will look for Bäume, but it's actually on index time. It'll index the occurrences of Bäume also as Baum, right? To be fast on search time so that it doesn't have to do any computation on search time. That's what the whole point of it is. It's everything, the heavy load is supposed to happen on index time, not on search time. And that's the stemming part of it. So it changes words based on their root. And that's language specific. And if we would need English stemming, we would also have to add the English analyzer, I think, which probably comes default with Elasticsearch. And then we would add another analyzer to it that would then be the English analyzer, because we don't want to mix those up, because as soon as you mix them up, you might have really, really weird outcomes. Like it might think that, I don't know, like a subword, I don't know, AD means something in English, and then it indexes that, and then it splits the Adler apart or whatever, right? So it's always important to separate those neatly, and that's why we've created all these different attributes or subfields. And then that's German. That's raw. Sort. I don't know. Maybe Flo can say something about sort. I'm not sure. Flo, do you know something about the sort analyzer? What that's for?
I think it's for sorting, but I
Sort
don't know. Yeah, I don't know exactly. I think something for sorting for dates and strings and numbers and so on.
Okay. Yeah, I have no idea either. But okay. All right. And then lastly, I want to talk to you about the auto, because the auto is the one that caused probably, I don't know, not most headaches, but it creates some overhead. I mean, the trigram is one that's really, really large, that indexes just a lot of data. And the auto indexes also very, very much data. Because what the auto does, especially with these long words, it makes it so that it starts at the first letter. I think we limited it to 2 characters. So it starts at the first 2 characters and indexes those. And then it indexes the next. And then it indexes the next. And then it indexes the next. And so on and so forth for each word, for everything. And thinking about it, I don't know, the trigram, the positive about the trigram is it stays always as triplets. This can become really, really large in the index as well, like long strings in the index, because we autocomplete to the very, very end. I think we've made a maximum of, I think there's something we set a maximum of 30 characters, just because German words can be so fucking long. And if you remove the last character of a German word, like if you look for car manufacturer and then this, if you mistype or something and it then doesn't find a hit, you can be sure that the client will call and say, hey, I want to have those search results as well, right? And then we have to, count how many characters, and okay, we hit up the max amount of our autocomplete, and make that larger. So currently, I think we have it up somewhere 40 or something, 30, 40 characters, which can get quite long. So our index is pretty large, and thus, the data in Elasticsearch. I mean, in a production environment like K-Center, I think, what are we raking up? 12 gigabytes? No, more. I think we're more than 12 gigabytes already in data. And it just gets more and more, obviously. The data just grows. And it's not really pure data, it's the indexes. It's all the indexes that are taking that room. But it's okay. Elasticsearch is still quick. Elasticsearch is supposed to work, it even says on the homepage, it's supposed to work with petabytes of data. It's just something to be aware of, that Elasticsearch is pretty great to hide all of that from us, that actually it has to dig through so much data. Okay. That's about the indexes. And what's important in Elasticsearch, realistically speaking, you want to combine sorting and filtering. But sorting of data, relevant sorting of your data based on the query term you input, that's where Elasticsearch really shines. That's where a lot of cool stuff happens under the hood that can be influenced, but that is actually really, really genius. That isn't just filtering of data. Because filtering of data and just saying, okay, I want to have 4 documents that represent, like, that have this GMB or whatever in their name, but not the rest, that's something that, in a way, a like query could also do of MySQL. But sorting that data in a relevant way, that's where it gets really interesting. And Elasticsearch does this through something called SCORE. So Elasticsearch actually, if we look at the 4 documents that we got back, so we got 4 documents back based on the GMB. And this one has a score of 3.9. Okay, that doesn't tell us anything yet, but let's just compare. This one has 3.9. This next one is exactly the same? No, 3.956, 3.950, 3.94, 3.38. That's different. All right, so this one is quite a lot less relevant, what they say. So we have, from all 4 documents, we have a 3.9 in the top, and then we have a 3.3 in the bottom, and we also filtered. So we have all in combination. We filtered our data, our 30,000 contacts, down to 4, and amongst those 4 that we found, Elasticsearch also gave us a relevance spec. It's basically like when you look for, in Google or something, or in Reddit is a good example. Reddit's, the search engine sucks, but they should really switch to something like Elasticsearch. But in Reddit, you also can sort by relevance if you find something, or do you want to sort by some other criteria? But if you sort by relevance, it's the system internally that takes your query term that you looked for and tries to be smart about it. Which in Reddit, they usually aren't very smart about it, but Elasticsearch is kind of smart about it, because what Elasticsearch does, it takes certain aspects into consideration in order to determine how relevant is this document that it found to your input query. Our input query was GMB on the client name property. This client name in the bottom, the one that has the lowest rating, 3.3 rating, is a very, very long name, where the GMB is in the very end. And that, if you believe it or not, that has relevance. Because the first that we found, the first hit, it's also pretty long, but I think it's less characters. Let's compare. So this is the one string, and this is the other, and I think already now we can see that the one is longer than the other. Okay, and this little difference makes it so that the first one is more relevant than the last one, because the GMB occurs earlier in the string. And that would be way crazy, but we can try that out. It's good. It's going to be interesting. If the GMB would be in the front, then it would say, oh, wow, this is super relevant, because we found the hit right in the beginning of the word. And if you would then combine a match query across multiple properties, which you can do, you can say, I want to find it in the client name, and I want to find it in the other name, and in the product name, and I want to find the GMB everywhere, or multiple things at the same time. It combines all of those queries against all of those properties with the algorithm to decide the relevance, and then together calculates the score for that document for this specific query. And that's then the score that shows you the relevance of that document. So if we, for instance, goes to something else, Schulte. So I'm taking the word that's right in the front here. Let's say Fleisch. Oh, it's a weird word. Let's go. Yeah, okay. Let's do it. We find 2 documents. The one has a rating of 3.9, and then the other also 3.9. Is this exactly the same? No, it's not exactly the same, so there must be some minor difference. I'm assuming just Schulte. No, it's exactly the same actually. Schulte and the other one? Also Schulte. So I don't see the difference between them. So actually their scores should be identical. Not exactly sure why they aren't. Maybe there's some influencing factor like the entire size of the document or something. I'm actually not sure because the names are 100% identical, aren't they? Fleisch was, yeah, they're entirely identical. So it doesn't make much sense that they would have a different score, but they're very close in score. So sometimes you have let's see, Fach. Let's look for that. Let's look for something else. Look for jobs because they should have, but not under client name, under name itself. Under name auto. Okay, so now we have 88 hits in my jobs index, which is a completely different index, and I'm going against the name property with the auto analyzer indexing. So as we know, where it splits up the word to be auto-completable. And here we found in the name property, let's see what we found. Fachinformatikerin, okay, where the Fach is the first word. And then, and again, it shows us only the first 10 hits, I'm assuming, because we didn't specify a size. So I'm assuming that, yeah, in the beginning, they're all like this. They all have Fach in the beginning. So that's not the best. Anyway, let's look at a higher size. Let's increase the size, and let's look at the last record. So let's add a size of 20. No, let's put in 88 because we get 88 results, right? So I want to see all results. And I'm going to scroll all the way to the bottom. And we're going to look at the last occurrence and the last job in the result. So the last one. Wait. Jumped all the way to the top again. Here. Created by, nope. Updated by, nope. Name. Okay, Aufsichtsperson, IMW, Universitätsabschluss, mega, mega long, Fach. Here it comes. Here's the word. And this also has a score of 0.9. And this is important that this is in comparison to other records. If I would look for this match query in combination with another property, and we haven't really learned about combining queries now, but we can do that in a little bit. But if I would combine this with something else to make this one of the only hits available, then the score might be completely different because the score is relative to the other documents found. And relative to the topmost document, for example, its score sucks. It's 0.9. It comes, yeah, the word is there, but it's not very, it's not very often. It's not very early in the sentence, and the sentence in general is very long. That's pretty much the 3 parameters. How often does it occur? How early does it occur? And how many other words are there, or how many other characters are there in that same string? And I think maybe some more criteria, but those are the 3 main criteria. So in comparison, if we check the first record again with a score of 4.7, so it's a pretty good score. It has the part where it occurred twice, Fach and Fach, twice. It has a pretty short name in general. So the ratio of its word against the rest of the characters is pretty high. And then also it occurs exactly in the beginning. So that's why this one earned the best score. And the other one earned the lowest score, even though both are hits. So the filtering happened. We only have 88, records out of I don't know how many, but yeah. So it filtered, but it also gave us relevant scoring. And once you start combining multiple queries against different properties, things become a little bit more interesting. Because this is now what Elasticsearch does internally. All we've added to it is the auto indexing. So this is something we did custom, adding the auto analyzer. autocomplete analyzer. That's something that wasn't there from Elasticsearch, default. We've added that, and that's really all that we've added so far. What we can manipulate, though, also is something called a boost. So say a user inputs the word Fach in an input field, and we want them to look for it as an auto property, but also find it raw, so that it's the entire string would be Fach, and also as trigrams, and also in a completely different property, like the client name or something. And then we would say, if it actually finds it in the raw indexing, we want that to be the highest possible. So that we want to be, that means we want that to influence the score the most. We want that to boost the score. If it finds it as a raw property in the name, like raw, right? That should be boosted a booster for the score. And boosters are integer values. 1 is just no boosting at all. It's just like it is. And then, you can up and up and up and up. I don't know what the maximum is. I think we've maximum used, 5 or 6. That's all we've ever used. But I think you can go pretty high. And the point of that is then you can say, even though the user inputs just the one term, because we designed the application, we know how we want properties to be related to one another in terms of relevance. The client, for instance, told us if something is found in the name property, that should have way, way higher ranking than if something is found in the username, for instance. If like the Fach would be a username part, that's, okay, we want that document to be found. Please include it in your search. So then we would include it in the search in the first place. But please put that booster really, really low. Like compared to the name should have like an 8 boosting, and the other one should just be default 1. And that way, that we as designers of our application can create a logic where certain properties are just more relevant than others. Something that Elasticsearch, of course, can't know about. Elasticsearch treats everything similarly if we don't tell it otherwise. So this boosting is a search time thing. It's not something on index time. It's something where we say on search time, when the score is calculated, because the score is also calculated on search time, since it compares documents amongst each other. Then we would say, okay, please, on search time, add these parameters or these sort of, boosting, not algorithms, but parameters into the score calculation, please. And then it does that. So I think next up we should write maybe a multi-match query. That could be interesting. However, I don't know the syntax. Let's see. Oh, multi-match. How does that work? Let's see. Multi-match. Ooh. Okay, makes sense, right? We're inputting one query, and we're saying which properties it should go and look for. So let's go with something a little bit difficult. Let's go with something. Okay, Arznei. And I don't know if that'll be difficult or not. And we want to first of all look in the name, and we also want to look in the name.auto, and we also want to look in the name.raw, and we also want to look in the client name, and so on and so forth. We don't find anything. What? Well, let's look in the trigram as well. Name trigram. Oh. Didn't I just have it in the name? Whoa. I really thought I just saw it in a name property. That's weird. Why doesn't it find it now? Name, auto, raw. Wait, let's. Here, oh, that's the client name. But I'm looking for the client name. Okay. I know what I did wrong. I'm just looking for the client name regular property. And the client name regular property, without our auto, trigram, etc., is just splitting the words, as we know. So it would look for the entire Arzneimittel word. But in order to actually look for the trigram of the client name as well, we would have to add all those as well. So we want to look for the auto and for the, I thought it was the name property, sorry, my bad. For the trigrams and so forth, so on and so forth. And then we now have 10 results. And again, here it has a rating of 3.4. And now it does its own, we don't boost anything now, right? So now it does its own calculation of what it thinks is most relevant. And it does that across all of those fields that we said. So name, name auto, name raw, name blah, 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 and finds the hits. And then it like does sort of a mathematical median sort of thing. And in this case, it found the client name Arzneimittel, and it also found it in the name, and this is probably going to be the highest ranking, because it found it both in the name of the job and then also in the client name. So this is like a jackpot. And then the next one is just going to be the name is not going to be anything with Arzt or Arznei, and then the client is going to be Arznei again. So this is the client name. And here we should also have a significant drop in the score. Let's see. 3.4 against 3.4. Oi, this is very similar. That's interesting. And let's now try our hand at boosting. So if we boost one of these properties, the name or the name auto, I think if we boost them, we should now have a different result in the score. So let's look at that. Multi-match boost. Oh, you can even use wildcard. So we could say, that could be cool. Let's see if that works. So name dot asterisk. And then I could save all of these. And then also would do the same on the client name asterisk. Let's see if I get the same results. I do. Very good. So this is already a nice shorthand. And then, oh right, this is the syntax for boosting. So what is this? Accent grave, the little roof thingy, and then the number of boosting value as integer. So let's say we want to actually boost the name. Oh, Jesus, what is this? Here. We want to actually boost the name by 5. So the name should have a much higher significance than the client. And hopefully, if everything goes well, this should influence the score of this, especially in comparison to the next one, because this had a hit in the name and also in the client name. So let's try it out. So this is a 3.4 still. The next one, 0.6. Ah, now we're getting a little bit closer to what I was thinking. So as you can tell, it didn't actually influence the score of the first one, but it lowered the scores of the second one relative to the first. Kind of cool that it worked. It's always a toss-up whether the stuff I do spontaneously here works or not. But if it works, it's always a good feeling. And I think if I lower this to like a 2, it should up this to something 2 point something, I would assume. Let's see. So this is still at 3. This is fine. 1.7. Okay, 1.7. But you see, this is just a way to adjust these hits based on the properties and the matches inside of these properties. So this is a multi-match query, and we actually use them quite frequently. We use them for, as a quick show and tell again, for all these input values where we have one single input that searches across multiple properties. Like, for instance, if I would look for Mitarbeiter or Mitar, then it looks for Versandmitarbeiter, but it also found it in the title tag, as it says here, title tag. Let's look for Medizin. That's a lot better, I think. And now it tells us, okay, it found 2 occurrences in the title right here. I found 1 occurrence in the client name. The highlighting is another feature of Elasticsearch, pretty cool. And then I also found it in 2 other properties, the title tag and the keywords. So in total, this one probably has the highest score of them all because it actually has 1, 2, 3, 4, 5 occurrences in 4 properties. So pretty good. And we've done custom boosting to also say, okay, the name is actually the most important of them all. Okay. that's the multi-match query and the exists query and the match query out of the way. The term query also, as it is just really matching the property one-to-one. And then there's some cool stuff with like dates and stuff. So you can, there's pretty cool math that you can do in dates, or date-specific math. Let me show you what I mean. So let's say, let's do some date stuff. Oh, you know what? Actually, I don't know the syntax. It's greater? No. Let's look at what it has here. It has child, match all, trace, boosting. Oh, boosting, okay. Multi-match, nested, prefix, span, term, wildcard, range. Range isn't range. I guess range could be interesting. So we want to find the range of date created where it is greater than, and then here you can just input a string. So for instance, 2017, 7/24, but less than 2017, 8/24, or whatever. So, and then it should find us a couple of records. Okay, 1,000 records where the date created is between those two dates. And if we check, it sounds pretty correct. It looks pretty correct here. And this can also be changed to like string input. Like there can become some crazy stuff in here. I think you can even say last Friday or some shit. Okay. Not maybe that much. But let's look at some date stuff, because they have pretty cool things there as well, I think. Compound query, that's not it. What's a span query? What? Matches spans near the beginning of a field. The span first query maps to Lucene span first query. Here's an example. Oh, I don't even know what this is about. But okay, never mind. Full text is not what we want. Term query is maybe what we want. Let's do a range query. Let's look what they have. So, here. Okay. This is now minus 1 day, or now, stuff like that. So you can have these relative date things. A little bit like what you might know now from that Java library. What's it called? Not JMonkey, the other one. Joda, the Joda time, where you can have just like some date math. Same you can have in Elasticsearch right in the query. So let's try this now. I don't get completion. This -d, not sure what that is for. Maybe to not interpret it as a date or something. To tell it like this is like a cool string. So this is telling me what has been created in the last day, right? So this would be, today and yesterday. I think it's like 12 hours, right? 1 day should be 12 hours minus. So it's doing some math. And so I would probably be able to say all the things that happened in the last week would be minus 7 days. And then I would have 6 records that have been created in the last week. And I think there's some more date math and rounding. So let's look at some date math. This is cool stuff. So plus 1 hour, minus 1 day. Round down to the nearest day. Okay, so this so what I said was wrong. It doesn't actually do just minus 24 hours. This syntax with the -d actually takes the entire full day. So it takes the full day yesterday and probably the full day today. And you can do that same thing, probably rounding down to minutes, months, and then minutes, and then hours, and so forth. Ooh, now plus 1 hour plus 1 minute. Yeah, this is cool. What is this? This is an OR. 2015, the 1st of January 2015, plus 1 month, rounded down to the nearest day. This is cool. So this is like a piping syntax. Okay, so as you can see, this is kind of cool what you can do with dates as well in Elasticsearch. And this is also not Elasticsearch. This is powered by Lucene, I'm pretty sure. So this is stuff that Lucene can do for you. Yes. So this is Kibana, and you can build queries here, but this is not actually the syntax we use to build queries. We use the Java API. And if we look on the homepage, Elasticsearch, there's a short interactive little menu in the bottom. I want to just show you what that looks like. Right here, where it shows us the different kinds of ways to do queries and to perform searches. And this is the one curl that basically we have been mimicking now with DHC or Kibana. And it should look a little bit, it should look pretty familiar, right? So you have query and then match, and then here's the property name and then some value. Aggregations we haven't at all looked at, you and I, but that's for another time. And this is familiar to us now. And this is also what the documentation will show us. Whenever we look for something, this is going to be the documentation. But the syntax we use in the application is going to be just a little bit different, which is the Java syntax. The Java syntax is just classes and builders around this syntax. And in the end, it outputs this exactly one-to-one as well. So for debugging, if ever you have an issue with Elasticsearch, you can just debug the search query right before you send it out, and then it'll look just like this, like I'm marking here. But the way you build it in Java looks like this. So you create a new search builder or search source builder, and then you make a query on it, which is the same as the first level query here. And then you say query builders dot match all query, and then you want to have, that's it's not the same as this match, because this is a specific match query against a property, but match all is, it just basically says find everything, find all the results. And then here's like aggregations, etc., etc. And then you fire this off. This is a search request, and then you say, okay, the search request should please use our search builder that we've created, and then you send that off with the client search request method. So it's just a wrapper, really, around this JavaScript object structure. And it makes it so that you have things like auto-completion. And that's a positive thing, that you can use something like auto-completion. So we prefer it. But for debugging, it's sometimes a bit hard to read and sometimes a bit hard to debug, especially when the documentation deviates and when the documentation looks like this. But this trick about debugging and using the log output of this search source builder or the search request, like between line 10 and 11, if you now would make a log debug of the search request, it would stringify that entire JSON object for you. And then it would just look just like in the curl or in Kibana. So it works pretty well to debug. And the advantage of having this auto-completion and compile time error detection in the syntax or in how we build our queries, things like where if we add a property in the wrong place, it'll tell us like, hey, wait a second, you can have a property name here, it's not a string here or whatever, just like compile time stuff like that. It makes work sometimes a lot easier. It's just sad that it deviates so much from the documentation. I think at one point they had like of their entire documentation, they had a Java version of that. But I think it's too much maintenance for them to have everything double. So yeah, I think that's really the reason. Another positive thing between 5.6 and 2.3 that we have is that the syntax for the querying hasn't really changed very much. Even though it's a lot of major versions in between, they actually haven't. They've improved things and made things a little better, but a lot of the things are very, very, very similar or exactly the same, actually. So that's nice. You don't have to learn too much new stuff. Some of the reason is probably because Lucene is built that way, and Lucene hasn't changed in years. So yes. Oh yeah, and one last thing, Kopf, which to inspect indexes and just get an overview, or not indexes, that's wrong pluralization, indices.
I have linked you the project, which is a fork.
Okay, cool. In Elasticsearch 2.3, it doesn't have to be with flow linked. Let's look at what he linked. But this we only need for Elasticsearch 5. Cerebro is an open source Elasticsearch web admin tool. Download from, access on. Okay. So you access it on a different port, just like Kibana, and then it runs against your current Elasticsearch and displays everything just like Kopf did before. I just want to show you what Kopf does. This is Kopf, and it shows me all my indices that I have locally. I have apparently 70 indices. That is approximately equivalent to having 70 tables in your database. Except that on localhost, across multiple applications, you have to start sorting things and prefixing things. So, for instance, I have prefixed things with kcenter_stage when I've wanted to debug against stage and like loaded all the stuff from stage to my local machine, or care_prod if I wanted to do the same with the production environment, and so on and so forth. It makes sense if we are running multiple applications, and Denny was actually the first of our employees who did it as well, to prefix their local indices right from the get-go. And I, as you can tell, haven't done this. So for me, it's like job application and contacts, and right there. So they don't have a prefix at all. And that makes it so that if I would create a second application, for instance, basics dialog, that also has contacts, then I have a naming conflict because both would be named contacts. So it makes sense to prefix them, call the one basics dialog contacts and the other kcenter contacts, and so on and so forth. And maybe down the road, ScoreMed contacts. Who knows? So this is just a way to manage your indices. And something you can tell maybe is if I look for contacts, I actually don't have an index called contacts, but I've been querying against this contacts for like this whole time. My post request search goes against something called contacts. And this is done through something called aliases. This is down here. Think about these as tags. Each index can have tags. They can also be tagged to multiple indices. And these tags are a representation of them for the HTTP requests. So I could go ahead and I could query the same thing with the _v1 as well, and it would find me the same results, and also with the _read, and it find me the same results, and this third one also contacts. So it's basically, it's aliases. It's different representations of the same index. But I can also go ahead and I can add the same alias to this index. And what that means is by using, say I would add contacts, just this contacts alias, to this one and this one. And then I would perform a search against contact search. What it would do internally then, it would actually look over both indices. So it would perform a search across multiple indices. And there is a practice with Elasticsearch where, as an example, if you have log data from a production environment and there's data is just logged all day long from the server, just, I don't know, errors or whatever, just log. And it's like thousands and thousands of documents of data, each document representing one log entry, for instance. What you might want to do, and what has kind of become common practice in the world of Elasticsearch, is to create an index for each day. So you'd have a log entry for October 13th, and then you would have another one for October 14th, and another one for October 15th. But if you want to look and search across all log entries, you could do that by using aliases. You could also do this by using wildcards. So you could say, I want to find, log entry _*, or you could use aliases. It's just giving you different alternatives and different options. And something that we use the aliases for is for reindexing purposes, because I haven't really touched on this so much, but Elasticsearch is a little bit different from MySQL in one more aspect. The mapping that we looked at earlier, and that I can also open here, the mapping of an index is looking at each property on that index, like country, and telling us, how it's mapped. So a string, and then the German analyzer is with the German analyzer, and the auto is with the autocomplete, etc., etc. And this mapping, however, is not created before the data is put in. You can do that, but it's not a requirement. In MySQL, it's a requirement. You have to create the column first and tell the column what it is. It's a varchar or what, yeah? This is a requirement before you can even input the data. That's not so in Elasticsearch. In Elasticsearch, say there's no mapping at all. and then you would index some data. It would create that mapping on the fly for you. Actually, how about, let's just do that. I have no idea how you create a new index. Jesus Christ. Elasticsearch. Quick start. Nee, nicht quick start.
You don't need to create the index, you just put something in there and then the index gets created.
That's so nice. Okay, let's do it. Cool. So I want to create something new. I want to call it Polto. And it's the index. So we have the convention where the index is plural and in the index is a type. We don't really use it. It's a sort of a substructure. So you could structure things, in a deep nested, a little bit like databases and tables. But the problem is the mapping is shared for all types within an index. But this is a little bit difficult. I'll get to that in a second. Otherwise, I'm mixing topics up too much. Let me first just post a document in here. So the way you post a document, I think, is no auto-completion. Oh, come on. Maybe I think doc. Let's see. Let's try it out. Let's just try it out. So city. Göteborg. One version of you is in Göteborg. And it's giving us created true and telling us that in the index Poltos, in the type Polto, it created one record. It doesn't tell us what the output is. It doesn't give us actually the data back. It just tells us like a kind of success. Yeah. And it also tells us that it did so on 2 shards. Shards is another matter entirely. Now I want to search for, I want to just see what's inside of this index now. So I would perform a search request. And now I get all records back. And it nested it inside of doc. So okay, so on post requests, I'm not supposed to put doc around it. But I think in put requests I am. So let's do another one, or another 2. Okay, and now I should have 3 Poltos. One with city Göteborg, another with city Göteborg, and a third with doc city. That one we could remove. And that's as easy as just doing a delete request to... Did I mistype a word? Okay, anyway. To the ID. So this is an auto-generated ID. Very similar to what you're probably used to from MongoDB. And this is not the one I want to remove. This is the one I want to remove. So you just send a delete request to that single poll. It's important to put the type in between. That's important. Okay. All right, so now I deleted it, and now if I search, I get 2 records back. Yeah. Okay. And if I now look at the mapping for this index, you can tell I didn't do anything in the mapping before, but already it's doing city, knows its type string, and doc is an object, right? The structure, remember, that's the object structure. So it's saying doc is another property that we found. You index a document that had this property on it, and inside of that was the city that was a string. So it's creating these mappings on the fly. But then once they're created, they're strict. So I can't now go ahead and I can't now make city an object where I have some key value pair. City or name or whatever. Yeah, let's try. And now it should probably give us an error. Okay, it's saying mapping parser exception, failed to parse city, illegal argument exception. So it's having a problem now. Yeah, it's saying, wait a second, you've told me once that city was a string, not an object, so I can't index this now. And actively and how we work with Elasticsearch, we actually leave it to its thing. We let it index the data based on its own merit. Except that we created this template where we say, anytime you encounter a string, we want you to use all this auto trigram babada. Yeah, we want you to index it this complex. And that's all we've done really to manipulate anything. Other than that, we leave Elasticsearch to gauge the types all by themselves. So if we were, for instance, to put in a date, and it supports a lot of date formats. So you can actually go ahead. I think, let's try, but I think you could even input a German date. So how do Germans write dates? Like, what's today? Today is the 13th October. Oh shit, I don't know if that works. No, I don't think that works. Let's try like this. Like, this is how Americans spell it, right? Like, so, like that. I have no idea. Okay, let's try. Maybe it found it as a date now. That would be really cool. Nah, this is a string. Okay, let's try another one. Last updated. And let's do it a little bit more proper. 2016. Is it dash? 10-13. All right, so now it did something. It says this is a type date and it's a strict date optional time epoch millis, right? So whatever format this is, it found something. And this is pretty cool because it can take, just plain JavaScript dates and put them right in there and everything works. And then you can do date math on this, all the date functions with the now and the minus and stuff, because it found out about this based on just this string. And again, there's some deviation, and you can input different formats, and it matches them against probably some sort of library that it has of common date formats. But yeah, so this is important to note that this is on-the-fly creation, and so there's sometimes things can go a little wrong, and then you're stuck with your data, and you can't index other data. Like, what if city was supposed to be an object, and everything is indexed as a string now? The way to fix that is to create a new version of the index, and that's why we have this versioning, where you create another version of the index, context v2. It's completely empty, you leave it completely empty, but in there you can explicitly set the mapping. It's just a post request, really. You just say, I want the mapping without any data. I want the mapping to be of a specific way. Like, I want this to be an object, for instance. And then all of a sudden, it won't accept strings anymore, only objects. And then you kind of force it into a certain way. Or what we often do also, we build these, like, building marshallers. We build mappers that map our objects into Elasticsearch, like JSONs, maps, I guess. And those we index. So we have a dependency to our Java code to already format our objects properly, so that then on index time, everything, Elasticsearch does smart choices about which mapping to apply. And if something is wrong there, like, very common mistake, we would say created by : and then just say just the ID of the user. And later we would realize, oh shit, no, we need much more than the ID. We need the name, we need the color, we need to input, we need to show a little user thingy in the front end. So we need much more data than just that. Because we usually take the raw Elasticsearch data and create the entire interface from the Elasticsearch data. So the Elasticsearch data needs to be quite complex because it needs to create the entire interface for us. So in those moments, the mapping has been number or integer before, because we just put in an ID in there. And now we want to change it to this object structure. And the first step then would be to create a new index and leave that completely blank and not touch it. Yeah. And then adjust the mapping to map a simple object instead of the just ID, and then re-index your entire data. So you would then, we created some methods, that iterate over all the context, over all the jobs, whatever object we're just now talking about. It iterates over them and then re-indexes them based on this mapping, based on basically the marshaller. So that's why we have these versions, because we realize over time our data morphs quite a lot. While we develop, while we work on it, we realize that it's not always the first time around that we know exactly how the data is supposed to look like. And so it evolves, and that's why we added the versions. Because otherwise, if we just had the context, we would have to entirely remove the version 1, then create the other index, because the indexes can't be named the same. The indexes can't be. You can just have an alias on both, but you can't have the same name on 2 indexes. So you'd have to entirely remove contacts 1 or contacts in order to create it again. And then you'd have to wait for the entire reindex to be done before you can before it is shown in the front end again. Because you would remove the entire index, and then for a while the data would be missing from the front end. And if you would do that on a production environment, sometimes that has happened, then your data is missing from the front end. So that's bad. So instead, what you can do is you can leave the read index. We've created the application so that the read and the write are separated. So the read is the one underscore read, the write is the default. And we just move the write over to the v2. So all new data is input into the v2, but it reads from the v1 temporarily until the reindex is done, for instance. And then we move the alias over and we delete this index. And then the user is none the wiser. He didn't even know that there was some change happening. Yeah, and so this has happened in the past, and it's a kind of nice workaround. Yep. I'm thinking, am I missing anything else? We haven't talked about aggregations, but that's, I think I've even made a video about that, so that's for another day. I think. Oh yeah, types. One last thing about types. Let's say I want to, inside of this Poltos index, create a different type. So we haven't talked about types at all, but it's basically like this deep nesting. You see here, Poltos, mappings, Polto. And then if I would create another one in here, another type, and I would use last updated and give it a completely different value, even though it recognizes it as a date now, I'm giving it just some garbage string. It's giving us an exception now because it's saying, wait, last update is supposed to be a different mapping, even though I'm using a different type though. So, and that's an issue because we've had occurrences where mappings deviated even though they had the same name. And that's why we've come to this. In the beginning, we thought we use the index as like the database. So it would look something like K-center. And then we would have the type as each individual table, so to speak. So job, contact, the client, whatever, yeah, what have you. But the problem with this is that then we would have these mappings, these global mappings, where last updated can only ever be a date, or updated by can only ever be an entire object if it's once been mapped like that, because the mappings are shared across types within indexes. And that's why we've separated indexes like this. And also they're a little bit more easily maintainable because I don't right now have like a list of types within these. I have nodes, I have indices, I have shards, I have docs, but I don't have types. It's not so easy for me to see all types within contexts. So I can't just like delete a type and reindex a type or something, but I can reindex an index. So the indices are a lot more maintainable in terms of just plumbing and getting them running and working on them and improving them, deleting them, everything like that, aliases, all that stuff. And types really aren't. So for me, there's sort of been like this question mark, what types are actually for? What do they really serve? What's their purpose? Because you can even run, I mean, the mapping you get against the entire index because the index is, it's global. The mapping is global for the entire index, as we just learned. And you also run a search against the entire index, not against the type. So the type is sort of like almost not very important. The type comes to importance in order to imagine you have, this could be interesting. Imagine you have a domain in your application that has a bunch of properties, and one of the properties is an actual type property. And the type is a string that differentiates between different kinds of, imagine your products in ScoreMed to be based on their product type, which could then be string, the string name could be chosen or something, based on their product type, the type could be created in Elasticsearch. That could be a use case. The data is all the same. The mapping for all the products would be the same. But the type differentiation makes it so that you can group data based on the type. And in my book, all that saves you is a term query, because whether you write get, let's say, products of type PVS, and then search, and then you do your query or whatever, yeah, in there, or you do get on PVS, get on all products, where you say, okay, you want to create a query, a term query, where the type needs to be PVS. You know what I mean? It just, yes, of course, this is kind of neat, this one-liner instead of this one, and that's maybe the advantage. Yeah, I mean, for something like that, that could be a use case for types, but the data, the documents inside of one index, they should be all the same. Values should be different, but the data structure should be the same across all documents inside of an index because of this mapping. I don't want to even call it issue, because of the mapping being the same by design. Yeah. Yep. I think that's it. Do you have any questions?
All right.
Except for a million.
Yeah, it was a pretty extensive workshop. No, I don't think I have any questions. I think I understood everything. I surely won't have this in my complete thing in my whole memory right away, but it was a really good kickoff, I think. And in the future, if I work with Elasticsearch, I think I'll at least remember the concepts that we talked about, definitely. So
That's great.
No questions, I think, at this stage.
Just your head just steaming a little bit.
Yeah, my brain is steaming, I think.
Yeah, no, okay, cool. What we haven't talked about at all is aggregations, but that's for, I think, another day. But it's a very cool thing about Elasticsearch. So remind me about aggregations down the road. Yeah, Flo?
I want to add the Elasticsearch, the Definitely Guide, or how it's called. It's a
The definitive guide,
online
yeah.
book, which is interesting and goes very deep.
It's really, really great. It's true. Let me see if I can find the link anywhere. Documentation. The definitive guide, yeah. This is so wonderful. I read the entire thing. It was so good. It's funny, and they write really, really well. It's
not a development documentation. It's more like a real book.
Right.
Yeah.
All right.
They really wrote this
I'll
well.
check it out.
Yeah, cool. All right.
Okay. Thank you a lot